Good evening, everyone, and welcome to this webcast entitled Analyzing Non-conforming Anatomical and Prosthetic Joints in the AnyBody Modeling System. My name is Michael Skipper Andersen, and I'm from the Department of Mechanical and Manufacturing Engineering in Aalborg University in Denmark. Before we start, I would like to show this slide here for everyone who has not managed to get sound so far, and I'll just leave this up for just a couple of seconds so the people who do not have the capabilities of actually hearing what I say now can actually get a chance to do so. So please be patient for a little bit. Okay, moving on. Before we also go on, I would like to remind you that there's actually a possibility to set up your screen, and to do this you need to click the sharing menu in the upper right-hand corner of your screen, and then you click on View, and afterwards you click on Auto Clip, and in this way the presentation should appear nicely and be fitted to your screen. I am your presenter today, so again, my name is Michael Skipper Andersen, and here with me I have our host, Arne Kies, who will be taking care of all the technicalities throughout this presentation. And if you have any trouble whatsoever, please just send a message, and Arne will help along. About me, I'm an assistant professor in the AnyBody Research Project at the Department of Mechanical and Manufacturing Engineering at Aalborg University in Denmark. I received my PhD in mechanical engineering also from Aalborg University in 2009, and in some work in overdetermined kinematics and parameter identification for musculoskeletal systems. And throughout the presentation, I would very much like you to, if you have any questions, and then please go ahead and ask them. And within this WebEx application, there is actually a possibility to do so. And the way you do this is by clicking the questions or getting up the questions and answers panel by clicking the question mark in your lower right-hand corner. Then you should get a small pop-up box where you can type in your question, and please do so. And then before you send it, please make sure that you send it to host, presenter, and panelist. In this way, both Arne and I will receive the message, and I will try to answer all the questions by the end of the presentation. The agenda for this presentation is that I will first give a very brief introduction to inverse dynamic analysis and use that as a starting point for what I'm going to talk about for the rest of the presentation. And the main focus in the presentation is about what we have termed force-dependent kinematics, and I will try to explain this method to you and give the motivation for why we actually want to use this method and what it's good for, and then to give you some idea of how to actually use the method for modeling. I will give a simple modeling demo in the AnyBody modeling system where we build a simple arm model. After that, I will show some preliminary results on a total knee replacement model using this force-dependent kinematics and contact forces and so on, and show you the results of that. And last but not least, I'll conclude on both the method and on the results in terms of the total knee replacement model. And last, we'll have the question and answer session. So the background for what we are doing here, and I'm sure most of you who have signed up for this webcast is aware of this, but it's musculoskeletal modeling. And what it is a model of the musculoskeletal system that we are interested in. So for instance, a human that I have shown here on the right-hand side. And a model like this consists of bones, joints, ligaments, and muscles. And then what we're interested in doing is from some motion or some scenario we want to analyze, we want to compute the internal forces. So the reaction forces within the joints, ligament forces, muscle forces, which are very difficult to measure in vivo. And a method for doing this is frequently done with inverse dynamic analysis, but there are other methods for doing this too, but I'll focus on inverse dynamics. So inverse dynamics, as I just said, is the idea that what we get as input to our model is of course, a model of the model, so the muscles, bones, joints, and the motion we are interested in analyzing, and also the loading on the model, so the boundary conditions that you can say. So the guy could be getting in and out of a car, or he could be walking, or whatever situation you would like to analyze. And then from this, you want to compute the muscle forces, activities, power, joint reactions, and so on and so on, and all the derived variables from this. This is the overall framework. To go to one specific thing, and that is joint modeling, then a typical approach in these inverse dynamic analysis models is to use idealized joint constraints. So for instance, a Revolute joint, a spherical joint, or any conceivable combinations of what you call holonomic constraints. And that's, for instance, in the models that you will find around in the literature on musculoskeletal models. That could be, for instance, a hinge for the knee, or a spherical joint for the hip, and in principle, a universal joint for the ankle, and so on. But the trouble is that there are actually very few joints that are well approximated with these idealized joint constraints. One can argue that the hip is to some extent a spherical joint, but that's also, if you don't go into the mechanics of it, then actually very few joints are well approximated by these idealized joint constraints. And what we basically assume is that within the model, that in all the directions that are constrained by the joint constraint equations, that there are infinitely strong reaction forces that can be recruited at any time without any deformation within the model. This, of course, is not always the case, or in reality is never the case. And the trouble with these constraint equation formulations is that it's very difficult, it's not impossible, to include an implant model to obtain also kinematics, because formulating the implant in terms of kinematic constraint equations in a realistic way is very difficult. So for instance, take a knee replacement example, which I have over here in the middle, where the knee is clearly not a hinge, because if you look at what the mechanical elements that we have here, then we have two implant parts in contact, so the femoral component here and the tibial component, and then we also have a patellar component that is actually sliding on the frontal part of the femoral component. And if we actually do not always have contact, or the contact shift from left to right, then formulating this with a kinematic constraint equation is very difficult. There could also be deformations going on, and also how do we get the ligament components in there. If you go to an anatomical knee, it's even more difficult, because there we have the cartilage layers, which is certainly elastic, and everything is really controlled in terms of the contact forces and the ligaments. So what we would like to do is actually model the joint in terms of the force elements that are in there, rather than having it be constraint equations. And the method we have come up with for doing this, we have termed force-dependent kinematics. And the reason for this name is that, of course, in an inverse dynamic sense, we have turned some of the constraint equations from before into being dependent on the forces that actually occur. So the idea is to include a possibility to model the joints in terms of force elements. And the way we do this is by introducing the forces, of course, take out the Revolute joint that would be, for instance, in the model that we had before, and put in some forces that replicate the joint we want to model. And then we want to compute the motion in those degrees of freedom where we have exactly force balance in the system, or a quasi-static solution. You could, of course, also go all the way and then compute it in terms of forward dynamics and get all the vibrations, and then we need to put damping and friction and all these components in there. But to actually speed things up, and also assuming that the vibrations are not so important, then there could be benefit in just looking at this average motion or the quasi-static solution. And one example is over here on the right-hand side. I will take it again. This is a simple arm model where we have modeled the elbow joint by two elastics, on the top one by two springs that are weak. So we actually have a deflection within the joint when the arm is moving, and we have an external load outside the hand, three muscles that are pulling. Then, because of the weakness of the springs, there has to be some deflection to actually have force balance. To then make the elastics very strong, we get something that actually replicates the Revolute joint. But this is, of course, a very simple example. I'll actually try to model this particular model now within the AnyBody modeling system. So, well, I will do that in a slide from now. I'd like to first tell you about the solution method for actually solving force-dependent kinematics. And the idea is that suppose it's the vertical and the horizontal translation of this joint, and assume that it's a planar motion, that we would actually like to compute in terms of the forces. Then what we do is that we introduce some extra motion. I have called them alpha S here. So that would be translation in the two directions. Then in the same directions, we also introduce some artificial reaction forces here called Fs. And then what we want to do is we want to find out exactly the position for alpha S in these two directions where Fs has to be 0, so that we don't need any external hand of guard to actually keep the model in balance. So the way we can solve this is that for any given alpha S, set up an inverse dynamic analysis model, and then we compute the muscle forces, reaction forces, including these artificial reaction forces. And then we wrap it into a loop that has to find out exactly at what position these reaction forces are 0. And throughout this step, we assume that the velocities and accelerations of these force-dependent directions are exactly 0, which is where we get to this quasi-static solution. So let's go to the AnyBody modeling system, and then I will try to do this arm example within the AnyBody modeling system. So what I have here now is the AnyBody modeling system, and I will load the model by clicking this button up here, Script to Model, and then I will open up a model view by clicking Window and Model View. Then what I get without doing anything else is just the model loaded, and it's not a sample before I actually run an operation on it. So I'll just run set initial conditions over here in operation. That will a sample with this initial condition. What we have in here is the arm from before, but we start out with a Revolute joint here at what we can call the elbow. And we have these two segments connected by a Revolute joint along the Z axis, and we have our three muscles and some external load here out in the point indicated here by the vector in black. And the script we have over here, just to give you a brief overview. In the top we have our global reference frame, which is the yellow part over here. We have the definition of our segments, so any sec upper arm with some attachment points on it, which would be any ref nodes, one for the elbow, and then we have three here for the three muscle attachment points. And then within the elbow, I have actually defined two extra nodes. I have called them attachment 1 and attachment 2, and we're going to use them later, which are actually these points that we are going to attach some strings to. So that's why they're defined already. We go further down, we have our lower arm, again on any segment. The same thing, we have the elbow node, we have a hand node where the external load is applied, and then we have three muscle attachment points, or muscle 1, 2, and 3. Moving further down to the code, we have an any force 3D, which is our applied load. This is a force applied at some point with 3D coordinates, and it's a force F here with 200 Newton in the minus y direction. If you go to model view over here, you will see that the vector here, the black vector, is pointing in the negative y direction in global coordinates. So this is where our applied load is. Skip the next piece. This is just the drawing of this particular vector. Then we get to our muscles. We have assumed in this simple model here, we have assumed constant strength muscle of where the three muscles each has a maximum strength of 2,000 Newton. And then I have attached near point muscles, which are muscles that go between points, between these attachment points that I had on my two segments, and they all refer back up to the same muscle model. So they all have the same strength, and then they attach between these points, muscle point 1, muscle point 2, and muscle point 3. The last little bit we have here are dummies. So the first one is that we have grounded the upper arm. So we have put in a standard joint between the global reference frame and the upper arm. I've just attached it to the elbow joint, but that doesn't matter. And then we have our Revolute joint. This is called the elbow here, which is rotation around the Z-axis in the local frames. And if you just look here, the local frames here for the yellow segment we have here, Z, pointing out towards me, and the same one here for the Z down here. And last thing we have is we have a driver. So we have a constant velocity driver driving the angle between the upper and the lower arm, or the elbow angle, to a constant velocity of pi divided by 40. And the last thing we've done is that we have set the reactions in this particular degree of freedom to off, which means the three muscles have to produce the motion within this joint. So the three muscles here in our model, they have to produce this flexion motion. Okay, so if I try to run it, first, and we have our Revolute joint, I will step through the analysis just for a couple of the steps here. Then we see that the arm is moving, and it's moving around the Z-axis. We would expect with a Revolute joint down there, and a flexion ankle and a constant velocity in this direction. So we're moving up in this way. Okay, I will stop here. So what we would like to do now is that we would like to get rid of our Revolute joint model. So the first thing I will do is I will actually just outcomment this one here. And then if I now reload the model, then I will be told that I have too few kinematic constraints to have a kinematically determined system. So that means in some other way I need to put in 5 new constraint equations to replicate what was there with the Revolute joint. And what I would like to do is that I would like to put in linear springs between these 2 points that we had from before. And then I would like to tell the system that it should compute the quasi-static motion or the force-dependent motion in these degrees of freedom. So the first thing we need are our springs. Go to my class list here, then I can get a list of all the classes within the system. And then I find any force, so which is the general way of putting in a force in any script. And I will call this one, let's give it a name, I'll call it string 1. And then it needs 2 things. It needs the size of the force, and then it needs a kinematic measure or a direction within which this force has to work. And the force, I want to be a function of the distance between the 2 points, and the measure I want to be the vector between the 2 points. So this I will put in. So the first thing, I'll just leave the force here empty for now, and then put in the linear measure you need, which is a measure that can measure the vector between 2 points. So any t linear is the one we need. And I will call this one, I'll call it linear, just to give it some name. And then it needs 2 reference frames, so the 2 points that we actually want the vector to be between. And the first one we want is, if I go to my model tree over here, click my model, and I find my upper arm, and go into my elbow. Notice here I have this point here I've called attach 1. And I will right click and then click on insert object name. Then I get this one, insert. If I then go on to the next line, I need my second point 2, which would be the node that's called attach 1 on the lower arm. So if I go over here in the model tree, find the lower arm, go down to elbow, and then find attach 1, and again click insert object name. Then I have a vector. This one will provide me with a vector between these 2 nodes, between the attach 1 on the upper arm and on the lower arm. So what I want my force to be is some stiffness times the length of this vector. And I will define any bar, and I will call it stiffness. So we actually have global access to it, and I will just for now set it to 1000, just start with the value. So the 3 components I want is my stiffness times the position in my linear object, so I write linear, and then within this linear object there is actually a position variable. So this one here with square bracket 0 will give me the x coordinate, and if I put in the next one for the y component, I get the second to get the y component, and then I put 2, then I get the z component. And then because we want the spring to pull whenever the vector gets longer, then we need negative values. We need minus in front of all these things. So this one was our first spring. The last little thing we will do, just to have it in the model view when we load it, is that we'll tell the system to actually solve it. And the way to do this is putting in, it's called an AnyDraw line. This one will draw a line between our two nodes. It needs two arguments. It needs to know the thickness, which I will just put in the value and know what it has to be, and then it needs a color, which you get by RGB, which is red, green, blue, and we will put 1, 0, 0, which will give a red line. So that was one thing, but I said I wanted two, so I will just copy this code and then replace the things I need to replace. And what I need to replace is that I want my vector to not be between attached 1 and attached 1, but I want it to be between attached 2 and attached 2. And then I, of course, need to call it something else. If I try reloading my model and look here, then now we have actually gotten two vectors, or we have gotten two lines between our two gray points in our model here. But we are still told that we have too few kinematic constraints to be kinematically determined. So we need to tell the system what it needs to do with these fast degrees of freedom. And what we will tell it to do is that we will tell it to compute the force balances. And the way we do this is that we have to include a kinematic constraint equation and then tell it that exactly this constraint equation has to be force dependent. And I need an anything equal simple driver, and I will So what this is a kinematic constraint equation that is in principle a constant velocity driver, but what I will do is that I will set the velocities to 0. So we get 0 velocities in these directions. I will call it something. That's the k equal. So, and we need 5 components because we were taking 5 degrees of freedom away with our Revolute joint. So we need 5 degrees of freedom. So we certainly need 5 components here. And also for the position driver here, we will put 0.0.0.0. And what we can actually use this for is for the initial guess on these force-dependent directions, but we actually going to end up that we will solve it without doing anything. But actually, if you wanted to change the initial conditions, then this driver position is the one we need. So what we then need to tell is that which degrees of freedom within the system is it actually that these force-dependent directions should correspond. And what we want is the translational coordinates or the center of the Revolute joint before, and then the rotation within the Revolute joint from before. So these 5 degrees of freedom. So we'll put in a linear, which will tell us that on the translation, the free translational component, I'll call it linear. And then I will again need to put in the references to that point. C, and then I need to refer to the elbow. I go out in my tree again and I find the elbow, so upper arm, elbow. And then I need, again, the other nodes, which would be the lower arm, elbow, which are the ones that the Revolute joint worked in. I'll try to do that. We don't need to dot that, that's a mistake. Lower arm, elbow, yep, insert. So those were the 3 degrees of freedom that have something to do with the translation. And then we need the 2 degrees of freedom that has to do with the rotation. So what we need is an anything rotational. I will put in an anything rotational, which can measure rotations. And I will call it rot. It's again between the same nodes, so I will just copy them up here from before, just to save the hassle of actually copy-pasting in it. Or clicking in the tree and putting them in again. And we will use the root axis angles, which are Euler angles in a given sequence, and we will use Z, Y, X. And the 2 degrees of freedom that we want force dependent to work on are rotation around the y and rotation around the x, and we will leave the z direction free because that is the one we want rotating around. And then to actually pick out these, we need to pick out these degrees of freedom, and we can do that with an any-key measure organizer. So I got it put in the wrong place. Oops, sorry. My bracket down here on the other side. And then what I need to tell is that I want these two components. Okay, so I will call this one, just call it organizer. And we want the second and third component, but because indexes are from 0, it's 1, 2. Then we need to tell that this kinematic constraint equation is a special one. It is one of these force-dependent kinematic constraint equations. And the way you say that is by specifying C type, and then you write force level. And it needs 5 components because there are 5 components now in our kinematic measure. So you need 5 of these. I'll just copy them. 1, 2, 3, 4, 5. So now we have told the system that these degrees of freedom in these kinematic constraint equations we want resolved by forces. And then we also need to tell that we don't have any reaction forces in these directions. So reaction type 2. And then we have to specify these for all the directions. So this tells the system that it cannot put reaction forces in these directions. The only forces that can come in these directions are the forces that we have supplied elsewhere within the model. So in our case, the ones that we have in our spring. So that was fine. Last thing to do is that if we go to our model and we find our study down here, it's called model study, and we go into inverse dynamics, and then we have a setting here that says four-step key on all, which actually tells the system that we want force-dependent kinematics. So we can leave the first part here, inverse dynamics, the force-dependent key on all equal to on. So now actually, if I got everything put in correctly, I should be able to load the model and see how that goes. It actually was successful. And we still haven't sampled the model, but if I now try to run it, so I choose my inverse dynamic analysis operation again over here, and I step through it, and get it to solve an active step, I will just stop right here. Then actually what we have now is that the mechanism has been sampled as it should, and then we have actually relatively large deflections within the elbow joint. And this is actually the deflection it takes to actually produce enough force in this direction to counterbalance the forces coming from the muscles in order for them to produce the correct movement around the joint. If I just run the animation for a little longer, we will see that the arm is actually moving around in this manner. Right. Go a little further here, and we will of course see that as we saw in the animation from before, it moves around. So, and it will of course move all the way up here to the end of the analysis, which is 99 times. So there we go. So now we actually have a possibility of controlling the joint in terms of the forces here. So if I go up and then find my stiffness properties again, and then I increase it. Before it was 1,000, now let's increase it to 1 million. So this means that within each of these linear force elements, it says 1 millimeter of deflection will produce 1 kilonewton for each of them. You should expect relatively small deflections now. So if I then run it again, then it is actually pretty much behaving as a Revolute joint again in here, because the deflections are to some extent very small. I will just run it here for a couple of times. Just to show you that it's actually resolving all 5 degrees of freedom with these two forces, and I will set the stiffness down again to 1,000, but then I will try changing the external load. So if I add 20 Newton in the Z direction, which is then out of the plane from the front, then we should get something completely different. So I will put in 20 here, and then I will reload. So reset and reload. Reload it, and then I will try and step it to the result, and I will rotate the view here a little bit, so we actually see it from the start. from the end up here. So now we actually have an uneven, or actually a rotated lower arm relative to what we had before, and this was completely controlled by the external load. Just to illustrate that this is actually, even with just these two simple springs, this is behaving much differently than just a revolute joint, and the stiffness is low. Okay. I think I will go back to the presentation and then show how this can actually be used for something more than just this simple toy example. So if I go back here, then I would like to remind you before I go on that if you have any questions, then please feel free to ask them, and I will very much like to answer them after the presentation. So thank you. So the model I would like to tell you a little bit about is a post-operative total knee replacement model that I've been working on for the last little while. The model is still a work in progress, but I would like to tell you the state of it right now. It's based on the data set that has been made available for this Grand Challenge competition to predict in vivo knee loads, and the data can be found on the SynCK website, and the data is distributed by BJ Frackley and Daryl Dulima. And the idea is that they give out all the data, so marker trajectories, doing different activities of daily living, gait, and also trunk sway motions and so on. They have measured ground reaction forces for the trials. They have CT scans on the prosthesis prior to surgery, as well as post-operative CT scans of the patient with the implant in there. They have electromyography of the select muscles, and then from this instrument, the prosthesis, they have measured medial and lateral compressive forces of the knee, and then the competition is, of course, to predict these forces as well as possible. The modeling approach I've been using is I've constructed the model in the AnyBody modeling system version 5, using this force-dependent kinematics approach that I just illustrated. The model was based on the lower extremity model based on the Klein-Horstman dataset, also known as the T-limb model, and it's in the AnyBody model repository. So what I did was that I replaced the Revolute Joint knee with a more advanced knee, and this one was based on the prosthesis geometry, and the prosthesis geometry was used to compute contact forces. I included nonlinear elastic ligament models, and then I introduced 6 force-dependent directions in the model. So I introduced the 5 degrees of freedom in the tibiofemoral joint, so all but flexion extension. So flexion extension was actually used to get the model to produce the motion we were interested in analyzing. And then I introduced 1 degree of freedom in the patellofemoral joint, which is in principle the compressive direction. So the patella is actually sliding on the front of the femoral compartment. The first thing I did was that because this Klein-Horstman data set is based on a cadaver and the data is collected on a different subject, we need to scale this cadaver-based model to actually fit the subject. And the approach I used for this was to include all the markers that were measured on the model, and paid very close attention to the ones that were on bony landmarks, so the ones that were on the aces, and the one that was on the sacrum, ones on patella, and on the heel and on the toe, because these are used to actually stretch and scale the model during a gait cycle, or actually multiple gait cycles, but during gait. And then the markers that were placed on the middle of the segment, so for instance the one up here on the thighs and so on, which were actually very undefinable in terms of where they actually went on the model geometry. I optimized those using an optimization-based method with the objective of minimizing the residual between the markers on the model and on the measured markers over the entire cycle. And so those were the design variables together with all the segment length within the model. So pelvis width and the thigh length, shank length, foot length, trunk height, upper arm length, lower arm length, and so on. So all these ones. During this scaling operation, I included the Revolute Joint Knee models, but it was only for getting the overall scaling of the model in place. As soon as I was done scaling, I was happy with that. I removed this Revolute Joint Knee assumption and built a more advanced one. The scaled model you can see over here on the right-hand side. The main thing to notice is the relatively small difference between the red and the blue markers, which are the model markers, and the markers that were measured in the data. After that, I used the CT scans, the scaled model, and so the CT scan of the implant parts alone, the CT scan of the implant within the subject, and then the scaled cadaver model, and then try to align everything to where I thought the implant went inside my model. And the red part you can see over here is the segmented implant from the subject. So the femoral and the tibial part were from the CT scan. The gray ones are from the implant scanned by itself. And then the bone parts here are actually the model, the scaled model that I have aligned in here. And this was actually to get the implant inside the model. When I had that, I needed to construct all the forces. So remember that force-dependent kinematics is all about modeling the joint in terms of the forces. So I needed to come up with the contact forces going on within the implant, and also the passive structures that keep the knee assembled. And the parts I modeled was the tibiofemoral joint, and of course also the patellofemoral joint. We look at the tibiofemoral joint first, then I approximated the femoral part by two ellipsoids fitted here, so we have two yellow ellipsoids, and the tibial insert I approximated by a point cloud. So two point clouds here representing the geometry of the tibial insert. Then computed contact forces between the ellipsoid and the point cloud, such that if they were not penetrating each other, there were no forces, and if the point was inside the ellipsoid, there was a force that was linear with the penetration depth. And then, of course, summed over all the points. Same was done both on the medial and lateral side. Then ligaments were modeled, so the medial collateral ligament and the lateral collateral ligament, the PCL and the oblique popliteal. The medial side was three force elements, and they were actually defined to wrap over a cylinder. The cylinder is not shown here, but it's actually wrapping over a cylinder to actually not get too large bone penetrations. And the lateral side were just line elements between 2 points. There were 2 points there. If you look at the patellofemoral joint, then this was approximated by sphere in contact again with a point cloud to represent the frontal side of the femoral part. And this is actually an exact approximation because the patella button is actually a part of the sphere. It's just in color. So there's no approximation in that. And then, because I only wanted to look at the sliding for now, I just introduced two artificial springs that actually pulled the patella into contact with the femoral part. And then I included a rigid model of the patella tendon. So the patella tendon is modeled to be infinitely stiff. There's one thing I should say more, I forgot to say about the tibiofemoral joint, is that I actually introduced soft linear springs from all 5 degrees of freedom to ensure that there's actually always some passive stiffness, because there has to be a well-defined static equilibrium at all times. There has to be changes in forces at all times. And due to the slack length required on the medial and lateral side, there's actually a place where this is not the case. So to deal with it, I introduced some soft linear springs. We should also say that the contact force computation based on STL files is actually in progress and should be done soon. So we don't need this approximation by ellipsoids and the point cloud. We go to results, then we have an animation here of the knee within the subject doing gait, and the motion looks pretty plausible. I will click it again in just a moment, but just to be sure that I don't overload people's networks out there, I'll wait a little bit. But a few things you should actually look for when I click it again is that just around toe off, right after toe off, there's actually lift off on the lateral side within the knee, and also because of the rough approximation of the frontal part of the femoral compartment, the femoral part at the points, there's actually some jumping of the patella on top of these points. So if I run it again, then you should be able to see this. So right around, it takes off now. There's actually lift off here on the lateral side, and you see a little bit of jumping of the patella on the model. We move to some results. Then start with some EMG. I have plotted 4 of the muscles, and I would like to start here on gastrocnemius. And what we have plotted is the muscle activity and the EMG over one gait cycle, so from 0 to 100. 10 gait cycles from heel strike to heel strike, and then both of them have been normalized to 1. So we can only look at them in terms of their timing, not in terms of their absolute values. If we look at the gastrocnemius, then they show very good correspondence in terms of timing. We have both of them starts around 10 to 20% into the gait cycle, and then they stop around 80%. The model shows a little bit of activity in the part of the swing, but it's not very much. If we look at gluteus maximus, then both EMG and activity show, and muscle activity show some activity for the first approximately 40% of the gait cycle, and not much throughout the rest of it. So that is also captured as well. Look at the vastus lateralis, then you see a good correspondence in terms of timing for the first 40%. Then around toe off, around 50 to 70, there is some activity for the EMG, but not in the model. But if you then go and look at what rectus femoris is doing at this given time in the model, then it actually has activity right at the time where it's missing for mastoid. So this seems that the model chooses to use rectus femoris here at toe off, whereas the subject has used mastoid. So this would be a muscle recruitment issue. We have 2 peaks here in rectus femoris, but this is actually due to the scaling of the graph to 1. There's actually very low rectus femoris activity within the subject. We go on to our compressive force results. Then here on the left-hand side, we have the total compressive force. The red is the estimated one, and blue is measured, again for 1 gait cycle. And the first thing we see is that the estimated force has the same trend as the measured one. So we have 2 peaks doing stands, and then lower activity, or relatively low force doing swing, and then it goes up again around heel strike. The other thing is that we see overpredicted forces. Both the first peak and the second peak is overpredicted in the model, and quite significantly actually by something like 700 Newton for both peaks for the total compressive force. So then look at the distribution between the medial and the lateral force. Then again, the medial force shows the same trend as the measured one. So we have again 2 peaks doing stands, and then lower activity doing swing. But we actually see quite a significant force in the estimated force, and this actually comes from the fact that the ligaments within the model are actually still stretched here. So the compressive force component seen in the estimated force comes from the ligaments in this case. If you look at the lateral force, then you start from 40 to 60% gait cycle, then both the estimated one and the measured one has the same peak. They go down after toe off and then build up again towards heel strike. So the last, from the 40 to 100% gait cycle, this lateral force actually looks pretty good. For the first part of the stance phase, there is some over-prediction of the lateral force in the model compared to what was actually measured. Another thing that you can actually see in the graph is that the lateral force actually goes to zero. So this actually completely shows that there was actually lift-off during swing. If you look at the joint translations and rotations, then these also look plausible. These were, of course, not measured within the subjects, but could give us some idea of what is happening. And I would like to focus on a couple of the graphs. If we look at the red one on the left, which is the anterior-posterior translation within the knee during the gait cycle, then right at heel strike, right after heel strike, you see that the tibial part is actually moving forward, so it's moving in the anterior direction, which makes sense because we are hitting the ground with the heel, and then there's some motion forward. And then throughout stance, it moves back again, and then when we get to swing, we get the tibia is moving forward one more time, and then it is actually stops up here with the plateau. And what is actually happening here is that we get the PCL activated, and that actually stops the motion during swing. The distraction compression, which is the blue one here, actually sit down and look about the shapes of the ellipsoid and also the point cloud, then this blue curve is actually a complete function of the geometries that are in context. The medial and lateral direction, the green one here, you see relatively small motion in the medial lateral direction, and that is because I put in a very stiff spring in this direction, because there are some edges on the implant, which will prevent very large medial lateral motion. Last thing in terms of the results here is that if you look at the blue curve on the right, which are the joint rotations, so abduction, adduction, it's the blue one, then we actually see quite a large abduction, which is in the negative direction here during swing, and this is actually the reason why we see lift-off, that the leg is actually being abducted quite a bit, and so much that it lets go on the lateral side. So with that, I would like to conclude. So first, the method. So I presented this force-dependent kinematic method, and it successfully both computed the joint translations, rotations, as well as muscle and reaction forces. And the method itself opens up new possibilities for detailed joint models in musculoskeletal models. Look at the total knee replacement model, then there was a relatively good agreement in terms of the EMT timing. The trends of the compressive force from the instrumented prosthesis was captured as well, but the peak forces were overestimated. And a reason for this could be that the moment arms within the muscles in the model is underestimated, but we're still looking and trying to understand why we're actually getting over-predicted forces. The model also showed plausible joint translations and rotations, but since we don't have them for this particular patient, they're very difficult to actually validate these ones. Then, of course, there's still more work to be done to improve the force predictions and get even better results. And with that, I would like to thank you for your attention, and then ask if there's been any questions. And if not, then I would like you to ask some now, if you may have some. And I'll just check with Anna if there are any